Okay, well, sometimes we treat random variables together because they may have an impact on each other, or for other reasons, they may just come together in a problem. So, in this case, we define something called a joint probability mass function if they're discrete. So, it's just what you might think it is. It's just the probability that one of them is equal to something and the other is equal to something else um, would give me a joint mass function. So probability x is little x, y is little y is just represented with one function that takes two variables. And it should be specified or specifiable for any two numbers. And then we call x and y jointly discrete in this case. So here's an example. One way, if you only have two, to represent this is in a table like this. And this is just a table. This is just pxy. Okay. One thing that must be true is that the joint PMF must sum to 1 when I sum over both x and y. And we have what's called a marginal PMF for x and y. So we define probability x equals little x. This is just p. We put a subscript of a big X here and a little x as the argument. And this would just be the probability x is little x. So x could be 0 or 1. So I'll put 0 or 1 here, and I get 0.4, 0.6. You notice it's not, I could say x has a Bernoulli distribution with p equals 0.6. It's true, but there's more information than that. X is also has a joint distribution with y. So okay, so in other words, there's information about if y is something, then x is influenced by that. So in this case, py equals little y. I'll put little p, big Y, subscript, little y, and here I have three choices, 0, 1, 2, and let's see, the probability y is 0 is I did this backwards. So this should be 0.4. This is if x equals 0, if x equals 1. Remember, these hold the probabilities. And probability y is equal to little y. Well, if little y is 0, I just add across the x's, so I get 0.3. If little y is 1, I get 0.3. If little y is 2, it's 0.6. Okay, right. All right, so these are just like regular PMFs, but there's more information, which is the information in the joint PMF, right? Okay, so these are obtained. So px of little x is just obtained by summing over all the y's, the joint. So notice in this, x is constant here. It's saying, so for example, if I wanted px of 0, I sum. So I would have p 0, 0 plus p 0, 1 plus p 0, 2. So I sum over the y's, and I keep the x constant. Okay, very good. And all there is just extra information about how x and y work with each other. All right. Well, if I want, then say I want e of x in this situation, e of x, I would just use the marginal PMF. So this is one way to do it. I sum over all x values, and I have x, px of x. Or another way is I could sum over both, put x here, pxy here. But you see, you get the marginal here, the x comes out, and these are the same thing. Okay, which we should generalize this. So, in fact, if I can find the expected value of any function of x and y, so suppose g is a function, say, from R2 to R, and then we want e g x y. Well, one way is to define w to be a new random variable, just a single random variable that contains the values that g of x, y is. So if I go like this, equals what? And we have the familiar two approaches. One is we let w equal g x, y. And then we could just say e of g x, y equals EW, and I can just sum. I'd have to first find the PMF of little w, so I'd have to find all these function values over all xy, and then I just multiply by PW of w here. So this would be the normal way, but again, just like with the sum, it could be hard to find all gxy. Notice x plus y is an example of gxy, but this is just more general. So we have the second proposition, which says e g x y. Well, this is EW, right? This is EW, which is what I have here. W, P, W, W. P, W, W greater than 0. Okay, but now, what can I do with that? What is PW of W? So this is just equal to the sum over W, over all possible W's that it could be, and times W. And what's the probability big W is little w? Well, that's the sum over all xy such that gxy equals w, right? And then I would just sum pxy over them. And that's pw of w. I just go over all xy where the function's equal to little w and sum the probability. So that gives me pw at little w. Okay, well, again, here I have gxy equals w. Here I have w. If I just bring the sum in here, I mean, I can do this in a couple steps, but maybe it's enough just to say this is the same as the sum over all xy. And now I just sense w inside here is gxy. I can just let it go. Gxy, pxy. I'm out of ink. Okay, so okay, got time. All right. If we go to our example, which we could maybe do an example of this. So for example, in the example we had over here, right, we have these. Let's compute, say, for example, find let's say x y squared for xy defined above. Well, I don't have to actually compute each of these ahead of time and find the PMF for each. I can just say e xy squared is equal to the sum over all xy where pxy greater than 0. And I put in little x, little y squared here, and here I put pxy. There were only 5 values that were non-zero here, And for a couple of them, xy squared are going to be 0. So I have to keep looking back. Right, so x is 0 for a lot of them, and y is 0. So I get only 2 that I need to do. So let's see. When y is 1 and x is 1, it's 0.3. So I get 1 squared times 0.3. That's 1, plus the other one would be when x is 1 and y is 2. So I have 1 times 2 squared, and that was 0.1. And this will give me the same thing. So this is just 1 times 0.3 and 1 times 4, 0.1 times 4. So I get 0.4 and 0.3, so 0.7. Okay, so that's the expected value of xy squared, a function of x and y. All right, well, a common function that we would care about is called the covariance of x and y. It talks about how x and y vary with each other. So we'll define that and then probably have to finish on the next video, but we define the covariance of xy equal to the expected value of x minus ex, y minus ey. Okay, so let's go to the next video for this.